All right, the rest of section 5.2 is coming up next. Multiplication and division of integers. And we talked about last time 3 different models of doing integer multiplication. We had this first one, and we actually had a different picture for it. I think I went to the end and created it. We'll see. Yeah, it looks something like this. So we had the example of -4 times -3. And we said we started with nothing. I liked this model really well. Mary suggested for us putting in positives and negatives in pairs until I have enough negatives to remove 3 or 4 groups of 3 negatives. And that leaves me with the 12 positives that are inside. We had the charged fields model that looked very, very similar down here, where I put in positives and negatives in pairs, and then I removed my 12 negatives, my 4 groups of 3 negatives. And then the last one was the number line model right here. And we all said that it was very difficult to sort of conceptualize that very well, but it is a number line model for this, the idea of going backwards and finding out where did I start at, what time did I start at. All right, so the next thing we're going to do, rather, is to talk about Theorem 5.1, which is integer multiplication. Is that Theorem 5.1? Nope, I'm on the wrong slide. Not quite. We're almost at Theorem 5.1. All right, so here's what this one is talking about. Integer multiplication says the following. If A is less than 0 and B is less than 0, then A times B is equivalent to the absolute value of A times the absolute value of B. And this is exactly where you guys keep going back to when you say, but isn't a negative times a negative just a positive? And that's what this statement actually tells you, is that yes, in fact, if you do have 2 negatives here and you multiply them together, because that's what A less than B and A less than 0 and B less than 0 mean, that when in fact you do multiplying, that's equivalent to taking the absolute value of doing so. Okay? And then the other fact here tells you what happens if one of them is negative and the other is positive. So we're going to arbitrarily decide that A is negative and B is positive. Or we could say that A is positive and B is negative. It doesn't make any difference which one's which. Then if we multiply these, that is, we multiply a positive and a negative together, we will end up getting the negative value of the 2 numbers which don't have signs associated with them, the absolute value of them multiplied. So that is a positive times a negative is a negative, or a negative times a positive is a negative. And we can justify that using these arguments with these concrete models, at least the first few times we do them, and eventually at this point we just have to remember, because we don't want to have to go back to a picture every single time, right? But the pictures do justify for us that that happens. All right, so properties of multiplication. We did this last time with addition and subtraction. First property is the closure property. The closure property says that if I multiply 2 integers together, like A and B, I get another integer, and it is a unique integer. The unique part is fine, but it's the integer part that's important, right? Integer times integer equals integer. All right? So this is the idea again. I'll do it one more time because I know some of you are still confused from even the last test where we did this whole numbers. The idea is that if we had all the integers floating around in this room, and we took 2 of them and we multiplied them together, it would be another number that's still floating around in this room. In other words, I can't multiply an integer times an integer and get a fraction. That doesn't happen. Because if I did, I'd have to open the door to the room and it'd be out in the hallway, or something like that. Commutative, you guys know what this means. If I have A times B, what does the commutative property say that that is equivalent to? B times A. Associative property says that if I have A times B times the quantity C, what is that equivalent to? How could I change this? Right, so we could put the B and the C inside the parentheses and the A on the outside, and that's equivalent. Now, both of these, B and C, commutative and associative, those look exactly the same. And in fact, so does A. Those look exactly the same as when we had whole numbers. Whole number times whole number is whole number. Whole numbers commute. Integers commute. Whole numbers have associative. Integers have associative. All this is the same. Identity. This one's also the same. What's the identity for multiplication? 1. This showed up on your last test too, didn't it? We talked about this. We have an identity element. So 1 is the unique identity element for multiplication such that 1 times A equals A times 1, which equals A. So if I multiply by 1 in any order, I end up getting back the same thing I started with. Distributive property of multiplication, we have this one again as well. Again, nothing new from whole numbers. If I have A times B plus C, what does that equal? Thank you, AB plus AC. And we had the equivalent that if we did it in the other order, that is, we had the addition part first with the parentheses, that we would end up with the same result, right? All right. This one, again, is a repeat. This is the idea that we have 0 is the unique integer such that A times 0 equals 0 times A, and what does that value become? 0. Okay, so the fact that you know and love that says if you multiply 0 by anything, you get back 0. You'll notice something doesn't happen that happened with the addition and subtraction. With addition and subtraction, we had a new property. Do you remember what the new property was? In 5.1? There was a new property for integers that we did not have for whole numbers. It was the additive inverse property. It was the idea that we said that if we had a number A, we now have its additive identity negative A, so that when we add the two values together, we get back to 0. Do you guys remember that one? That was a new property, and we talked about the fact that we didn't have that before because we didn't have negative numbers before. Notice we don't have any new properties here. Any idea what the missing property is that we're kind of looking for and would like to have? The new property that we added in the last section was the additive inverse, right? In this section, it would be nice if we could have the multiplicative inverse here. That's the missing one. That really is. That is the one missing property that we do not yet have. Why don't we have it?
Two numbers, when they're multiplied, they don't cancel out. Like, they're not opposite.
Okay, so let me give you an example, Morgan. And you tell me what we would say the multiplicative inverse should be. What is the multiplicative inverse for 5?
We would like it to be -5.
Well, we don't want it to be -5. That would be the additive inverse. Okay, so 1/5. We would like it to be 1/5. And we would like that because when I multiply 5 and 1/5 together, I get back the number 1. So why don't I have this property yet? We don't have fractions yet, right? Have no fear, we will have fractions in math too. All right? We do get to have those there, and when we encounter them, we will have that one additional property that we're sort of missing at this point when we get into fractions in math too. All right? But we don't have it yet, so we do not have this property that allows this yet because we don't have fractions yet. All right, so we're going to identify what properties are displayed in each of these 4 scenarios. The first one says -2 times 3 is an element of I, which is the integers. What property is that showing? That's closure. When I multiply 2 integers together, I get another integer. What property is B? -4 times 0 equals 0. That's the 0 property. I'll put property on here, on all of them. If you leave the word property off, it's okay, but they are the 0 property and the closure property. How about the third one? Negative 2 times 3 plus 4 equals negative 2 times 3 plus negative 2 times 4. That is the distributive property. And the last one, negative 2 times 3 equals 3 times negative 2. That is the commutative property. So any questions about the properties? No? Okay. There really shouldn't be. I mean, there's not anything new in that section. They just are the same things we did with whole numbers applied now to integers. All right, next theorem. Our next theorem is talking about this idea of negatives. So that if we have an integer a and we're talking about negative 1 times the quantity a, that is equivalent to talking about the quantity negative a. It's not a very exciting theorem. Would you agree? Not real exciting. But one of the things that this does for us is it allows us to talk about what is the number in front of a, because it doesn't really look like there's a number there. And the number in front of a right here is what? It's negative 1, right? The negative on the outside. So there's a negative 1 issue there. We can also talk about what happens, or the equivalent of what happens when we have negative number times a positive number. So if we have negative a times b, this is the same as having negative times ab. And if we think about it from the theorem 5-6, that should make sense. We've taken the number that was negative a, and we've understood that to mean that it's negative 1 times a. So then I can group the a and the b together with the associative property, right? Group these two together instead, and put those inside the parenthesis with the negative on the outside. So this is sort of an application of the associative property. And we can do the same thing here. And we'll actually write it down cleanly now that when we multiply negative a times negative b, what do we get? AB. We wrote it down with this absolute value idea before, and we understand now of that idea being that we end up with the negatives canceling out. That's our language that we've been using. All right, one more theorem, and one more theorem here talks about the distributive property with subtraction. If you have a times b minus c, or b minus c times a, this is an extension of the distributive property. So what is a times b minus c? AB minus AC, very good. And B minus C times A? Yeah, it's the same thing, AB minus AC. The distributive property works with subtraction, in other words. Okay, our last 4 slides all have to do with division. Now 3 slides, and then we've got our homework slide. All right, definition of integer division says the following. For all integers a and b, a divided by b is a unique integer c such that a is equal to b times c. So in other words, let's do just a real quick example. 40 divided by 5 equals 8. And the reason it does is because 40 is equal to 5 times 8. And that's usually the way you first talk about division with children, is you say, remember those multiplication tables? Let's just think about them backwards. Right? If I have the number 40 and I want to divide by 5, well, what's the other factor in the multiplication table that 5 times what equals 40? And you can often describe it this way as well, that if you rewrite it, you can rewrite it as sort of this missing box. And sometimes you'll see even textbooks use question marks, fill in the box when we're talking about division in this way. All right. Definition for divisibility of integers. If a divided by b is a unique integer, then we say that a is divisible by b, or equivalently, b divides a. You've seen that before, haven't you? You guys loved it in chapter 4, didn't you? You loved it so much you're going to take a test on Monday over it. That's those division properties, and we've seen that notation. And I know some of you don't like that notation very much, but just remember and write it down if you have to, that this actually says b divides a. In other words, a is divisible by b. That's what that means, not the other way around. So this is not the slanted division symbol or something like that. It means divides. Definition of less than for integers. I don't think I even have to write anything on this slide. For all integers a and b, a is less than b, and we write that with that symbol less than, if and only if there exists a positive integer, I shouldn't say integers, positive integer k, such that a plus k equals b. And we have seen this before. We did this with whole numbers, that if we're talking about a being less than b, and we were to add a little bit to this side, we should be able to get back to the integer b that's missing. And that's what you mean when you say, for instance, that -2 is less than 5, is that there is some number that I could add to -2 to equal 5. And if I did, in this case, what's that missing number going to be here? It would be 7. So that's the k value that this is referring to. There's always some missing number, and it's always an integer because we're working within the integers and we have this closure idea. All right, and then for integers a and b, a is less than b, or equivalently b is greater than a, if and only if b minus a is equal to a positive integer, that is b minus a is greater than 0. Okay, so let's write that one again. We'll still use my -2 and 7. So -2 is less than 7. If and only if the 7 minus the -2 is greater than 0. And what is 7 minus -2? 9. And all this is actually doing when we do this b minus a is it's talking about the distance between them. The distance between them is a positive distance if we do it in this ordering, right? Obviously, if I do -2 minus 7, this isn't going to give me the ordering I'm supposed to be using, so I'm going to get a negative. But the distance between -2 and 7 is actually a positive number, so this would be 9. All right, we have one more theorem to do. Our last theorem talks about what happens with these inequalities. All right, if we have x is less than y and we have a number n, and we add that number n to both values, then our inequality still stays a less than inequality. Okay. We've seen this once before. I think I've talked about it in this way. I'll say it again in case I haven't. This would be like me standing here and Carrie standing beside me, and we're, how tall are you, Carrie? 5'9". I'm 5'4", so Carrie's 5 inches taller than me, right? She's taller than me, so she's the y in terms of our height. I'm x. So if we both put on 3-inch heels, we're both now 3 inches taller, but we still have the same relationship that I'm still shorter than Carrie. That's all that this is saying, is that if I increase each piece of these, I've still maintained the same less than relationship that I had before. All right, the next one, if x is less than y, and I multiply each of them by a negative number, 1, in this case I'm using just -1, what happens to my inequality? It switches, and in fact you had a homework problem where where we talked about this up here on the board still, in fact, number 20, right? So if I multiply by a negative number, it switches it around, yeah. All right, the next one says that if I have x is less than y, and if I have n and n is positive, then if I multiply x times n and y times n, the inequality stays the same. Okay? So imagine using a projector, or imagine your shadow. We'll use shadows. I think that works a little bit better. So again, if I were standing and Carrie were standing next to me and we had the sun creating a shadow for us, then we would still have the issue that that sun would create a shadow where my shadow is going to be shorter than Carrie's, because I'm shorter than Carrie, right? That's what a multiplicative factor does. So if my factor, let's say it's a factor of 2, say n is equal to 2, then my shadow is twice as long as I am tall, so is Carrie's going to be twice as long, so my shadow is still going to be shorter than Carrie's shadow. That's what multiplication does. And the last one says if x is less than y and n is negative, right, so this is negative, then if I multiply negative n, not negative n, I'm sorry, n times x and n times y, but n is now negative, what happens to the inequality? This one switches. And all D is it's a combination of B and C together. C says that I should be able to multiply them and the inequality stays the same. but now all of a sudden my n value isn't positive, it's negative like it was in part B, which switched the inequality, so it switches the inequality down here in part D as well. Okay? All right, here's the homework, and then I'd like for you to get into